Okay, the recording has started. So welcome everyone. This is another morning with the Brussels Institute for Advanced Studies, BrIAS. This is a joint program between the two sister universities in Brussels, Université Libre de Bruxelles and Vrije Universiteit Brussels. So the first interdisciplinary research team of BrIAS this year is the past, present and future of food, climate and sustainability. Christian Hermans, this is me, I'm your host this morning. I apologize, but I'm voiceless. Your microphone is well set. You will not get more sound from me at the moment. So I am the program director on the ULB side, and my colleague David Canella, who is also online, is a co-director. It is my pleasure to introduce you Professor Natsuko Kobayashi from the Graduate School of Agricultural and Life Science at the University of Tokyo in Japan. In 2009, Kobayashi-san obtained her PhD in agricultural science from the same school. She was then JSPS, so Japanese Society for the Promotion of Science. She was a JSPS postdoctoral research fellow. And in 2013, she became assistant professor at Tokyo University. And since 2018, she is associate professor. So Kobayashi-san teaches radio ecology and agricultural radioactivity. She is also responsible for a large training course on radioisotopes handling during experimental procedures. Kobayashi-san has published more than 60 papers in peer-reviewed journal, and she is member of the Radio Plant Physiology Laboratory. Tanoi-san is the director of that lab, and if there are some members from that lab following us, we say them hello. Natsuko has a long-standing expertise on radionuclide tracers in plant physiology, like radiocesium, which is the topic of our talk today. So during the presentation, we ask you kindly to mute your microphone. Should you have questions, you can write them in the chat. I know sometimes people don't have that option. So if you cannot write your question in the chat, you will just raise your hand in the end, and then you can unmute your microphone. Then the floor is yours, Natsuko. So you can share your slides, okay. And it is really a pleasure to host. And unfortunately, circumstances are these, and we wish we could have you here in Brussels, but it is our pleasure now to listen to your talk.
Thank you, Christian. So can I start my sharing screen? So is it okay?
Yes, it is.
Yep. Okay. Now I will start. Okay. Maybe good morning, everybody. I was actually supposed to be in Brussels by now, but I had to give up on going there because of the stricter immigration control in Japan. It's a pity that I cannot meet all of you in person, but I'm glad to have the opportunity to talk to you like this. Now I'm speaking in Japan here, and you are here, and maybe in the morning, and it's going to the night, just at this picture. And I'm in Tokyo here, about 200 kilometers from Fukushima Prefecture here. So today I would like to talk about what the researchers, farmers, and governors did in wake of the nuclear accident in Fukushima in 2011. I will start my talk with a short explanation of what happened 11 years ago, since I guess some of you were just in elementary school 11 years ago and may not remember much about the news at that time. The disaster began with a massive earthquake on the afternoon of March 11, 2011. The epicenter was here in the ocean trench, and the maximum magnitude recorded on land was 7. The earthquake caused tsunami with a wave height over 10 meters and killed over 1,500 people and left over 2,000 missing. Japan has traditionally experienced many earthquakes, but what made this earthquake so special was the fact that it led to the nuclear accident. So 15 minutes after the earthquake, tsunami hit the nuclear power plants located along the coast. The power plants lost all of the electric power and the core could not be cooled. As a result, hydrogen explosions happened during March 12th and 15th due to the core meltdowns. The hydrogen explosions caused the release of radionuclides into the atmosphere. After the explosion of the Unit 1 reactor on March 12th, the contaminated area expanded for about 10 days, like this, depending on the ever-changing wind direction, like here, and precipitation. So in this time, the wind is going to the ocean, but sometimes they are going back to the land, like this, and the contaminated area expanded. So the resulting final contamination situation is shown here. Many kinds of radionuclides were released, but when considering the half-life and the amount of released, the radionuclides we had to concern in terms of the agriculture was radiocesium, especially cesium-137, having 30 years of half-life. So I will talk about what has been done to protect food from radiocesium contamination. I'll focus on 3 topics today, which is regulation barriers in Japan, and peat contamination situation, and rice. The first story is about regulation barriers. In fact, we did not have regulation set for domestic agricultural products before this accident because there was no significant radioactive contamination in Japan. Therefore, we needed to make it in a hurry. I mean, the radionuclides in food must be regulated. Can you tell why? Because radionuclides emit harmful radiation, a kind of high-energy beam. So, such as alpha or beta or gamma rays. The energy of radiation is so high enough to eject orbital electrons. So, ejection of orbital electrons causes disruption of chemical bond and ionization of the molecules. This reaction happens in any molecules, including DNA and water molecules in our body. In case of water molecules, it split into protons and very active radical molecules. So this radical is also harmful. So the exposure to the radiation leads to cell damage. Then to consider about the regulation values, we should understand quantitatively how harmful radiation is to the human body. So these are the typical symptoms of radiation injury referred as early side effects. For example, if you received 3 gray energy from that radiation, hair loss occurs. This is because the cells in the hair follicles are damaged. Then how much is 3 gray? Actually, the energy received by a person exposed at the point of 1.5 kilometers from the explosion center of the an atomic bomb is about 1 gray, like this. So you can assume that we will not be exposed so much radiation in our normal days. What we are concerned about is the risk of increased cancer rates from much lower dose of exposure, like here. Although the effect on cancer can be unclear when the exposure dose is so small, we should assume a linear relationship between the exposure dose and the risk of cancer, like this. And there is one more thing we need to know when considering the regulatory values. That is the background radiation. In Japan, on average, we are exposed to 0.0021 sievert per year, which is roughly equivalent to 0.0021 gray from natural radiation. So these values vary depending on what you eat, like this, and where you live, like this, and other factors like smoking. So taking all these things into consideration, Japanese government set a provisional regulatory limit on March 17th, like this. These values were set with the aim that the additional exposure to food should not exceed 5 millisievert per year. And the reason why the value in Japan was lower than EU is because the contamination rate of the food was assumed to be 50%, which is higher than in other countries. And 1 year later, the regulatory limits were lowered, like this, because the upper limit of the additional dose was lowered to 1 millisievert per year, while the assumed contamination rate was left unchanged. Anyway, in accordance with these regulation values, pre-shipment inspections were intensively conducted. So this is the result of the inspection in 2011. In total, about 45,000 food items was inspected, and 2,600 items exceeded 100 becquerel per kilogram. In total, as expected from the contamination situation, most of this food was produced in Fukushima, here, and Kanto region, especially in northern part, here. Now let's look at the results in more detail. So this is a part of the results of inspection in Fukushima Prefecture within 5 years after the accident. During the first year after the accident, many vegetables were found to be highly contaminated, here. This contamination was mostly due to the direct deposition of radiocesium on the edible part. We also found that the use of contaminated farming equipment, which was left outdoors, can cause the contamination of agricultural products. In rainy season, the adhesion of highly contaminated soil particles was also cause contamination of vegetables. we have learned these factors, and in general, radiocesium content in vegetables has gradually decreased lower than the regulation limit of 100 becquerel per kilogram. So this is the story about the regulation values in Japan. So nowadays, standard for the general food is 100 becquerel per kilogram, so as not to post 1 millisievert a year additionally. So the next topic is peach. Peach is a specialty of Fukushima Prefecture. In terms of harvest, Fukushima Prefecture was the second largest in Japan in 2010. The main production area for peaches in Fukushima is the northern part of the prefecture, where the contamination was middle level and was not under evacuation order. So many farmers continued to manage their peach orchards, concerned about the contamination of the peach fruit to be harvested in the summer season. So here I will introduce what happened in peach orchard based on the investigation by Professor Takata. So this is the peach growing calendar in Fukushima. So you can see the flower bloom in early spring, followed by the fruit growth, and the mature fruits are harvested during summer season and shipped. And the nuclear power plant accident occurred in March here, when the peach trees were in dormancy and there were no leaves on the tree. So this fact led to the hopeful expectation that the peach fruit cannot be contaminated, because the pathway of fruit contamination was assumed in this way, based on the report after the Chernobyl nuclear accident. The contamination in the air can cause the Fourier absorption and translocation to the fruit. Direct deposition on food can also be occurred. But in case of Fukushima orchard, this pathway cannot work because there were no leaf and no fruit at the accident. Then the second pathway can start from soil contamination. In this pathway, root uptake can be the entrance of radiocesium. To understand the impact of root uptake, we usually calculate transfer factor, which is ratio between fruit and soil. If the radiocesium content in fruit is 100 becquerel per kilogram, and the radiocesium content in soil is 10,000 becquerel per kilogram, the transfer factor is calculated to be 0.01. In fact, transfer factor of peach fruit is usually less than 0.01. Given that the soil contamination more than 10,000 becquerel were rare in Fukushima, we thought the peach cannot be contaminated so much. However, through the emergency survey, it turned out that the peaches contained higher concentration of radiocesium than estimated, like this. So Professor Takata tried to find out the reason. he noticed that there were peach trees with its ground surface covered with a sheet in the university's farmland before the accident. In these trees, the direct deposition on trunk and branches was the only source of contamination. So he grew these trees together with the trees without ground cover and harvested the fruit in the summer. The soil contamination level was apparently higher in the tree without cover. That is obvious. But the fruit contamination level is almost the same in both trees. It was suggested that the root uptake cannot be the main pathway of radiocesium contamination in fruits. The surface of trunk and branches was probably the entrance of the radiocesium. Then the distribution of radiocesium inside the trunk was analyzed. The outermost bark tissue was contaminated, of course, and furthermore, radiocesium already penetrated and reached the phloem here, and vascular cambium and sapwood containing xylem tissues. The bark does not seem to be a perfect barrier against the entry of radiocesium. Then, how will the radiocesium that penetrated the trunk move in the following year? Do they translocate to the fruit? To know the amount of translocation, trees with direct deposition in the orchard in Fukushima was transplanted in 2012 to the non-contaminated soil and grew until fruit matured. Then it was found that the most of the radiocesium remained in the old trunk and roots, but 3% was translocated to the newly developed organs, including fruits. This translocation can contribute contamination in fruits and also can be referred as a pathway of radiocesium exclusion from trees because these leaves are going down after fall. Finally, the effect of root uptake was evaluated in the orchards in Fukushima. The non-contaminated trees were transplanted into the orchard, and fruit was harvested in that summer. Then the transfer factor was found out to be the level of minus fourth power of 10. This value is relatively small, but cannot be ignored. So how did the peach contamination go after that? Happily, peach radiocesium content was decreased gradually after 2011. In this tree, radiocesium content at harvest was almost 1,000 becquerel per kilogram in dry weight base, but it was approximately 80 becquerel in 2015. This is far below the regulatory limit. So it's good that they didn't destroy the peach trees. So we assume that the low transfer factor and decreasing translocation can lead to a gradual decrease in radiocesium in fruit. So finally, I will talk about rice. So rice is a staple food in Japan. Although the consumption has been declining, rice maintains the #1 in terms of a single agricultural crop consumption. Subsequently, the value of production of rice is very high in Japan. In Fukushima, as many other prefectures, rice sales are the main source of income. So this is a rice farming schedule in Fukushima. When the accident happened in March, the rice planting had not yet begun. So to start or not to start planting was the matter that needed to be considered urgently. They were worried that the reputations of rice from Fukushima would be damaged if the rice exceeding the regulatory limit was harvested. In order to avoid producing rice with radiocesium exceeding 500 becquerel per kilogram, a guideline was decided that rice should not be planted if the radiocesium in the paddy soil exceeded 5,000 becquerel per kilogram. Based on the result of previous studies showing that the transfer factor of rice is less than 0.1. So rice planting was suspended also in the areas under evacuation orders, this area. So what was happening in the autumn of 2011? Unexpectedly, in September, inspection of 1,724 rice samples, there was no one exceeded 500 becquerel per kilograms. So in October, the safety declaration was issued by the governor of Fukushima Prefecture, and shipment started. But 1 month after that, in November, very unexpectedly, one rice sample exceeded 500 becquerel per kilogram, so shipment was stopped in this area. And from November 17th until February 4th, 2012, emergency inspections of 280,000 samples were done, and as a result, 310 samples exceeded 500 becquerel per kilogram. So, in which paddies those contaminated rice harvested? It was found that those paddies were spotted throughout the districts, like this, here and here and here. So the primary investigation indicated that the potassium content in soil, rather than the soil radiocesium content, was strongly related to the radiocesium content in rice grown there. A lower potassium content in the soil will result in the higher radiocesium content in rice. So, one of the causes of rice contamination should be the potassium deficiency in paddies. In fact, it is well known that potassium and cesium are similar in chemistry and share similarities in their behavior in living organisms. The membrane of the cells that make up living organisms are lipid bilayers, and when ions pass through them, they pass through dedicated ion transporters. Here is one of the potassium transporter proteins, this one, in which potassium ions are now entering through the pore. Looking at this pore from above, we can see that the potassium ion is surrounded by the oxygen atoms of the carbonyl group. This condition is chemically very similar to the potassium ion in the aqueous solution, surrounded by the water molecules. And this can be one of the reasons why potassium transporters efficiently transport potassium. And hydrated cesium ions is very similar to potassium ions. Actually, cesium ion can pass through some of the potassium transporters. So rice potassium transporter OS-HAC1 is such a transporter mediating cesium uptake. We evaluated the contribution of OS-HAC1 on radiocesium uptake by cultivating the mutants on the contaminated soils. It was clearly demonstrated that the lack of OS-HAC1 inhibited radiocesium uptake in rice, while the potassium content was only halved. This means that there are several transporters working for both potassium and cesium uptake in root surface, and OS-HAC1 can be the main molecules working for this process. So in potassium deficient condition, radiocesium will pass through OS-HAC1 more easily because the competitive ions are absent and cause radiocesium contamination in rice grains. And in addition to this mechanism, potassium deficiency has some effect on cesium distribution in rice shoot. This is our lab experiment using cesium-137 as a radiotracer. We cultivated rice either in potassium deficient or sufficient condition and separated into organs and visualize the radioactivity. Then, not only was the signal intensity higher in potassium deficient rice plant, but the distribution of the signal was also altered. The radiocesium was accumulated more in the younger tissues, such as flag leaf and culms and ear. We don't know so far what is the underlying mechanism, but we assume that potassium translocation system is the key to understand this observation. So here is another cause for radiocesium contamination in some paddies in Fukushima. It is clay mineral content. In this terraced paddy field, the rice produced in the second field exceeded the regulatory limit. The farmer managing this terrace paddy field practiced low input farming and referred as the outstanding farmer. He applied mountain stream water, which contains enough minerals to grow rice instead of chemical fertilizers. In fact, the potassium content in soil was very low, and the distribution of radiocesium in rice grown in this paddy field indicated they were under potassium deficiency, so radiocesium is accumulated in the newly developed tissues like this. But potassium deficiency alone did not explain why the radiocesium contamination was occurred only in the second field. When we examined the physical properties of the soil, we found that the clay content was, for some reason, lower in the second field, comparing the first field and the third field. Clay is another key player affecting radiocesium uptake in plant. This illustration presents the structure of clay crystal of 2-to-1 type silicate layer. The sheet structure of tetrahedral molecules and octahedral molecules overlap, and ions get stuck between, resulting in the structure of discrete elite layer. In this elite particle, there are 5 sites where cesium ion can adsorb. In current model, frayed edge site is suggested to be the largest cesium adsorption property. The radiocesium absorbed by clay minerals hardly removed, and plant root cannot uptake them. So fortunately, the clay content of the soil in Fukushima Prefecture was found to be high in general. So for the raw potassium soil, potassium fertilization aiming to increase potassium content higher than 25 mg was recommended. So 25 mg is here. And if the clay mineral content was low, the risk for the radiocesium contamination can be higher. Thus, we need to be careful. So in this case, additional potassium fertilizer was also recommended. And other than the 2 factors, we have learned that irrigation water can cause radiocesium contamination in some cases, and the surface soil decontamination instead of removal was also effective to reduce the rice contamination. So we learned a lot from our investigation. And following the detection of unexpected contamination in 2011, Fukushima Prefecture has been inspecting all rice bags since 2012 to ensure the safety of the rice. To check 1.2 million bags during harvesting season, they developed the conveyor belt type instrument, which is capable of checking that the values does not exceed 100 becquerel per kilogram in only 30 seconds measurement. So these temporary inspection sites have been set up in various places in Fukushima Prefecture. And this is the record of the inspection of all rice bags. In 2012, they found 71 bags that exceeded the regulatory limit, but after 2015, no contaminated rice was found. So there is all 0. So therefore, after 2020, they changed the inspection method, and now they are focusing on some specific area. So this is the summary of my presentation. For rice, soil potassium content and clay mineral content affect largely on rice contamination levels, and no rice bags was exceeded 100 becquerel after 2015. So the inspection of all rice bags ended in 2019. So that's all for my presentation. Thank you. So can I stop my presentation now?
Voilà, oui, désolé. Thank you, Natsuko. Can you hear me?
Yes.
Okay, yes, I had an issue with the sound. Thank you. So there is a question from Frank in the chat. Can you read the chat, or do you want me to?
Chat. Yes, what the graph of contamination food? Is this? What the contamination food a function of times taking only cesium or all residues? This is only for radiocesium.
Yes, this is related
yes.
to the slide you
Yes.
show earlier.
Okay.
So I'm gonna say it so that people who know. So was the graph of contamination of food as a function of time? So the one for 5 years taking only cesium or all radioisotope, for example, iodine into account. Maybe you can.
Yeah. I understand that. And it's too to go far
First,
away. This one.
Okay.
I think this one.
Frank,
Yes.
if you like, you can unmute your microphone and talk. Yeah? We are not that many people.
That's the graph I was talking about.
Yes. I will explain a bit more. So this is only for the radiocesium, and actually the regulatory limit is set in taking into the consideration of all other radionuclides, including strontium and also iodine. So
Okay.
yes, we are just monitoring the radiocesium.
Yes, I was wondering whether short-lived isotopes could have explained the rapid decrease in the first weeks.
Oh, I
but,
see.
It's only cesium, of course, it doesn't play a role. Thank you.
Yeah.
Okay, so the next
And the second one
is from Christopher. Christopher, he's a BrIAS fellow. He's working at Orlando University on citrus.
Citrus, okay.
Do you think that potassium allocation impacts the seasonal dynamics of peach cesium content?
I see.
Again, Christopher, if you like to unmute your microphone, you may speak.
Maybe you are indicating this graph, I suppose.
Yes, that's right.
Yes. And maybe you mean, oh, where is my pointer? Sorry, I lost my pointer. Where is my? Oh. Anyway, so there is a seasonal variation, and the concentration of radiocesium in peach fruit is highest in the youngest fruit, and this is because peach is growing. So this is a kind of biomass effect. So the concentration radiocesium and also potassium is decreasing according to the peach growth. Is it okay for your question? So yes, so this allocation is related to the potassium movement. Yes, as you
Christopher
indicated.
says, got it. Thanks. Another question from Frank. In your slide on staple food, one sees major changes in food between 1965 and 2005. Did the trends continue?
Is this?
I guess.
Yes, that's the one.
Did the trends continue? The trends. Trends. Yes. You mean trends? This one?
You see, for example, rice is going down. Is it still going down, or the livestock products seem to reach a plateau? There are really dramatic changes in the food content
yes,
of the Japanese population.
Yes, so our culture on the food consumption is changed dynamically after the World War II. So we take a lot of wheat and maize and such a European food. So the rice consumption is decreased dramatically after that, and now decreasing. and actually it keep decreasing slowly until now. But still rice is a staple food in Japan.
Okay, thank you.
Then there is a question from Neil. Thank you for a very interesting presentation. Do you know whether runoff of neighboring plots, for example, forests, contributed to contamination in specific rice plants?
Runoff, you mean the irrigated water is coming from the next paddy fields, for example?
Yes.
Again,
yes.
Yeah.
I have never heard about that.
Okay. Yeah, I was just wondering because I know that a lot of effort has been done in removing the contamination of certain plots, but forests, for example, were untouched, and therefore it might be that that the cesium re-enters the paddy fields through the runoff.
I see. So we are some of the researchers keep monitoring the runoff and the contamination level runoff, and I think the contamination level is very, very low. So that cannot be the cause of contamination of rice grains nowadays. But instead, there are some particles. For example, the mushroom seeds. I don't know the English, but they are coming from the forest, and sometimes they cause the contamination.
Okay, interesting.
A similar question from Margot. She's asking if the rice fields were flooded.
Flooded.
Again, Margot, if you like, you can unmute your microphone.
Yes. What I mean with flooded, I know that some cultivation practices cultivate rice in these terraces which are underwater. Wait. Hi, this is me, by the way.
Hi.
And I know that then the ammonium content in solution is also very important, not only the potassium content. So I was wondering if the soil is aerated or not, or if it's under flooded conditions.
For the rice paddies?
Yes.
Yes. Until summer, they are flooded, completely flooded. And after summer, after the year was developed, the irrigation is stopped, and they are changed to the dry field.
Okay. And so do you see these seasonal patterns then in cesium uptake, or is it just constant? Or don't you monitor the cross or the rice plants multiple times in the year?
You mean the sorry, one more time.
Sorry.
I will change my slide to the correct one. I cannot. Sorry, where is my pointer? Oh, here. Can you see this?
Yeah.
So they're completely flooded. And then here's some water is remaining, but maybe the irrigation is already stopped. And
but
after
the soil is still saturated.
Yes, not so dried.
Okay. Yeah, then it might be interesting to also monitor the content of ammonium.
Ammonium in the
cations in solution.
In solution, sorry, I don't know. We are just measuring the radioactive materials.
Okay, and the potassium level. Okay.
Sorry.
Okay, no problem. That was my question. Thank you. Bye-bye.
Bye.
Then the next question is from Mark. He's surprised to see how fast the consequences of the accident and contamination of food were diminishing over time, while the isotopes were still present. So he's asking, are there conditions the local food producers should do in order to make the isotopes remain bio-unavailable?
Okay, I want to see the first consequence. Are there conditions that local food producers should do?
Again, Mark, you can unmute, you can talk about.
I see.
I just wonder. I saw your graphs, and I saw that in the food and after about 5 years or so, you didn't really detect a lot of radiation anymore. So, but the isotopes must be there, so they don't disappear. So they are likely to become bio-unavailable. So are there conditions? So are farmers warned that they should not, I don't know, make sure that the soil doesn't become acidic, or that they have to use different tilling methods, or have to use different irrigation methods to make sure that the isotopes that are currently unavailable for uptake become available again?
Oh, well, we have never think about that that way. So
because the contamination didn't disappear, huh? The contamination is still there. Huh?
Yeah, but in the living area, domestic. How can I say, the area people were working or living, the decontamination physically is proceeding. So mostly they are removed from those living restriction.
How can you remove such a large-scale deposition?
Yes.
I mean, it's in forest, it's everywhere. How can you? I can't imagine you can remove that.
Except forest, yes.
Yeah, except forest.
Except, yes.
Yeah. But even agricultural fields, are they then? Is the top layer taken off?
Yes.
It's impossible.
Yes,
But where are you going to leave all that?
Yeah, they removed from the fields, and they are accumulated in the some area around the Fukushima Daiichi nuclear power plant. But now they are going to move again to somewhere.
Yeah, but it can only be for the most contaminated regions, because if you would calculate how much waste you get, that is you can make Fuji Mountain out of that. So you can only do that on a very limited scale, very close to the nuclear power plant. But the area of contamination is much larger, of course. I was just wondering whether there's any, because some parts are not accessible yet, but other parts have never been closed. So, so are farmers then told, well, you should be careful, because if you do agriculture like this, then there's a higher risk of cesium ending up in rice again, whereas if you do it in a way.
But by the way, have you ever heard about those release from the, for example, clay particles?
No, I was wondering. I'm not a specialist on that, but I can imagine that this binding, this immobilization to clay is not. It can be reversed. It's not. I would think so, but I'm not sure.
So here is Neil. So do you know something about that?
I can add a little bit to what he is already said. So first of all, the removal of soil is gigantic. What has been achieved in Japan, very large areas have been remediated. If you ever go there, it's unbelievable to see all these bags that have been filled and removed to other parts. they have concentrated not on the most contaminated areas, but first actually did the less contaminated areas so that they were freed up for agriculture again, and then went slowly to the more contaminated ones. I don't know how they are going to deal that. I didn't follow it up now, but I know that even in the most contaminated areas, they're also remediating by removal the 5 centimeters of topsoil. And then on the other hand, it is known that cesium over time really the bioavailability goes really down by the fact that the cesium will really intervene into these clay layers and the bioavailability really decreases.
Yes.
And is that irreversible?
That is partly irreversible. Yes, it's not that it's like an equilibrium in that whatever you take away from the soil solution will be replenished by cesium that is within the clay layers. Yeah.
But if plants would become potassium deficient, for instance, would they not then get to the cesium? I would think they would actually.
Yeah, they will. The cesium will if the potassium really goes down. So the fact that you add potassium, and that is also something that is done for the agricultural land. The fact that you add potassium as a fertilizer really also reduces the amount of cesium that is taken up, and that is something that. But to explain the curve, so the curve that went down faster than the fact that the cesium contamination is going down, or that you could expect from the cesium contamination, I think for Japan specifically, the remediation measures been taken, as well as the fact that cesium really reduces the bioavailability. But I think Margot can tell more about it because that's the topic of her PhD.
Oh, really?
Yes.
So Margot was writing in the same sense, potassium fertilization and soil excavation, but you can give your
also
point.
tillage practices. And now there's actually research going on also in Japan about adding zeolite minerals to the soil, mix it with the soil, and in that way try to countermeasure these contaminations.
But our experiment performed maybe 2012 and 2013. The result indicates the effect of zeolite on the reducing the radiocesium contamination in rice is because of the potassium supply from the zeolite, not the capture of the rice. So
over a long period of time, it can set free potassium, because if you fertilize your soil with potassium, then the plants will take up the potassium indeed, but it will be like a spike of potassium that you add, and you have to add a lot of fertilizer, and it costs a lot of money to countermeasure and to do this over time. That's why they indeed try to add the zeolites, which are saturated with potassium, and then this potassium can exchange from the exchange complex and set potassium free over a long period of time. Indeed. But yeah, adding zeolites to the soil, I believe it's also a very expensive practice.
That's right.
If the other option is to put all the soil in bags and wait for the decay time, that's even worse. So,
So in the end, does it work to do phytoremediation, phytoextraction, or is it useless?
Until a certain point, but the plants cannot take up all the cesium. It's the difficult or tricky part is that these clay minerals can very selectively absorb cesium and hold it very tightly. So for this, I don't know if there's any countermeasure yet which can solve this issue.
And phytostabilization.
I don't know what phytostabilization is.
To grow plants on soil which are heavily contaminated with radiocesium.
Is it the same thing as phytoremediation?
No, I'm asking, is it useless to draw some strategies like this to have plants continuing to grow on contaminated soils? Or
maybe you need to give the definition of phytostabilization.
My definition is to have plants covering the soil. At least we stabilize the red. So if nothing is growing, then you have wind, and it can move the pollution further away. So that's my definition. Although I'm not in the field, that's what I.
No, and I think, for instance, those forests, they are biostabilized or phytostabilized. So there is no removal. The contamination stays at the site. There's no runoff, at least little. So that would be stabilized. But of course, all the agricultural fields, they are not.
Okay. Then Marco had a question on the rice transporters, potassium transporters in rice. So he's asking, how did you choose the one involved? By the way, great presentation.
Thank you.
So how many potassium transporters, and how did you?
Yeah, there are so many, maybe over 60. There are so many potassium transporter in plant, and why we are targeted on the OS-HAC1 is because this is the homologous to AT-HAC5. That is the potassium transporter in Arabidopsis thaliana, and that is very famous for its absorbing capacity of cesium. So we focusing on the OS-HAC5, HAC1, and it works. So it's a bit surprising because OS-HAC1 has so much impact on the radiocesium uptake. There may be some other transporters contributing in the radiocesium uptake, but in fact, OS-HAC1 has huge impact.
Okay. Then Mark wrote a comment on phytoremediation makes only sense if the bioconcentration factor of the remediating plant species is over factor 10. Otherwise, you create a lot of low contaminated waste at huge cost and no income for farmers. I see David wrote fishery, chitin, and algae as well. I think it was related to one comment. David, you are there?
Yes. Thanks for the nice presentation, Natsuko. No, I mean, normally also they are even let's say creating this new kind of new bioremediation concept by using this kind of fishery waste to, let's say, mobilize the radionuclides, and so taking this chitin and algae as a sort of bioabsorbance molecules. I mean that, and so they have a huge abundance of these, and then they are using a lot. So together with the bag system, so that's also lower down the costs of the remediation. Like it was pointed out, that is like a huge cost, but actually by using this kind of wastes, they're mitigating the costs, and they are actually replenishing the normal microflora that is helping. Yeah, but I'm reading now the comments of Mark Hart. I guess I will leave it to the floor to this discussion because this is a bit more centered to the topic. So Mark, please take the floor.
Okay.
No, I just mentioned that you need an awful lot of space if you're going to excavate and take off topsoil. That is, I know Japan is a big country, but it's quite it's not very rich in agricultural land. So with a large population, so the demand of agricultural land is very high. So you want to store this at a place which is not an agricultural field. I think that will be difficult. So I know that they have excavated, yes, but that is not unlimited, and it is very expensive.
They are actually storing or moving it towards the reactor. So they're putting it on the most contaminated parts. So they're using it actually even to damp some of the to make sure that some of the spots that are less that need some extra soil. They use that soil, which is less contaminated than the contaminated parts closer to the reactor. They use that soil therefore. So they're moving it all towards the reactor, or that's at least what they did, because I heard now that they're looking for another solution to move some of the bags too. But that was the first aim, was to move it all towards the reactor itself. It's a gigantic operation.
Yeah, I fully agree. No, I think it's, and the question is, was it really needed to excavate all this? If you see that there is a lot of it being absorbed by the soil, then you could also have decided, okay, we wait 5 years, that is tough, but then the release to plants is so low that it's acceptable again. But okay, yeah,
but
it's an interesting topic. Sorry.
Margot is suggesting to Google Fukushima soil bags, and we can have a clue of the current situation. Okay, are there more questions? No? So then we thank again a great presentation, and we hope that you can come anytime soon in Belgium. That was really a pleasure to have you and to show these aspects related to radioisotope, which is one facet, the BrIAS topic of this year.
Yeah.
So clap hands.
Thank you.
And so now you can get some rest and sleep. Maybe it's too early to go to bed. So it's been 8 hours.
Yeah, it's 7 o'clock in the evening.
Okay, so you can have dinner.
Yeah.
Thank you. Thank you, everyone. So for the BrIAS Fellow, we see each other tomorrow for the lunch at UAE. And then we will have 2 BrIAS talks in the afternoon, starting from 2. You can join us directly at Salle Solvay Building NO, or you can follow the events online. So I recommend you to check the Facebook page where you have all the information on the program, or the CPBL website where you have all the announcements as well. Thank you, everyone, for that great interaction. And see you another time on the BrIAS channel. Bye-bye.
Bye-bye.